let's give this a little bit of context. Okay. I want to review conceptually what we did when we were first analyzing AC circuits. Okay. So when we were first analyzing AC circuits, we had our circuit in the time domain. And what we wound up doing was we wrote and solved differential equations. And in solving those differential equations, we wound up determining what our time domain results were. So for those of you that had me for circuits 1, this little signal flow diagram thing right here effectively represents what we did prior to learning about the concepts of phasors and impedances and all that kind of stuff, right? For my students, I typically work a simple RL circuit where we write a differential equation around our loop, add the voltages together, and then do a ton of trig identities and all of that kind of good stuff to wind up getting our time domain results. Take somewhere in the ballpark of 25 to 45 minutes, depending on how many questions and all that kind of stuff get asked. Okay. And then I tell you, we're never going to do this process again because working in the frequency domain makes the math much, much easier. Okay. So now let's add parallel to this path our frequency domain, right? So how we adjusted our solution process is as follows. We transform our circuit from the time domain into the frequency domain. We did that by representing all of our voltages and currents as phasor voltages and currents. Working in the frequency domain, all of our differential equations now look like simple algebraic relationships. And then we use these algebraic relationships to get our frequency domain results. And then lastly, we transformed our frequency domain results back into time domain results. And it did not particularly matter which path we chose, either working explicitly in the time domain like we have on top, or if we hopped over to the frequency domain to do all of our analysis because the math was easier there. We get the same results either way. So we have these two kind of parallel universes of circuit analysis, one in the time domain and one in the frequency domain. And working in either domain allows us to get the answer that we were looking for, but the math was quite a bit easier when we worked in the frequency domain. Okay. So when we were working in the frequency domain, we were explicitly dealing with steady state sinusoidal excitation, meaning that all of our voltage and current sources were sinusoidal sources that existed forever, all the way from negative infinity out to t is equal to positive infinity. Well, now we're going to look at realistic sources, right? Which could be sinusoids, but they're zero until we turn them on instead of having their value forever. Or we might have other types of AC sources, or a better way to put it would be time varying sources. So we're going to do the exact same thing, but instead of working in the frequency domain, we're going to work in the S domain because that's where Laplace transforms live. Okay. So let's first define our Laplace transform. So the mathematical definition of a Laplace transform is as follows. If we have a function f of t, the Laplace transform of our function f of t will be the integral from negative infinity to infinity of our function f of t multiplied by the exponential function e to the negative st dt. And we're going to call this transform capital F as a function of s. So on the left-hand side, we have time domain. This is our method from going from the time domain into the S domain, and then our result of this operation is a function in the S domain. Now, this is the definition of the Laplace transform that you guys probably learned in Math 245 for those of you that have had it, and will be learning in Math 245 for those of you that are currently in it. I'm not sure what the pacing of that class is, so you could already be there. We are not really concerned with the Laplace transform as a mathematical entity. So we don't really use the bilateral Laplace transform, which is what this thing is, because it stretches all the way from negative infinity to positive. We are going to use the unilateral Laplace transform because every circuit and every signal that we can physically realize exists only after t is equal to 0 when we turn things on. Okay, so the first change that we're going to make is we're going to replace that bottom limit of integration from negative infinity. Started out at 0 because we are only going to work with causal systems. Okay, we're going to make one other modification here. So instead of just calling this 0, I'm explicitly going to call this 0 minus. Why am I going to set the limit of my integration from 0 minus to infinity? What's important about t equals to 0 minus? Why does that matter? So we include the initial conditions on voltage drops across capacitors and currents flowing through inductors. Because if we start the limit of our integration at t is equal to 0 plus, that's only applicable if our energy storage elements are starting from 0 energy storage. And that's not always the case. So this is what our definition of the Laplace transform is going to be. So let's talk about this guy S here. Okay. So S is the complex frequency, and it is defined as sigma plus j omega. So our complex frequency is in and of itself a complex number, where sigma, the real part, tells us how things are decaying, and omega tells us how things are oscillating as they decay, right? So for a system where sigma was equal to 0, we would have a pure sinusoid, right? But what we're going to see is sinusoidal excitation that is exponentially decaying as our transients die out and all of that kind of thing. So not all signals or systems have a Laplace transform. In order for the Laplace transform to exist, the integral needs to converge. Okay, so the convergence condition is as follows. The integral from 0 minus to infinity of the magnitude of f of t e to the negative st dt. Sorry, that should be a t and not a tau. Will be equal to the integral from 0 minus to infinity of the magnitude of our function times the magnitude of e to the negative sigma t times the magnitude of e to the negative j omega t. We're just splitting that s up into its constituent parts of s is equal to sigma plus j omega dt. And now we're going to play around with this just a smidge. So what is the magnitude of e to the negative j omega t for literally any value of t? What does e to the j omega t represent? Right. So what's the magnitude of a sinusoid? Will be 1 because there's nothing out here, right? So e to the j omega t, if we were to look at it on a polar plot, is literally just the number 1 being rotated around the circle, right? And the speed of rotation is simply omega. So e to the minus j of an angle is just 1 unit wide, and then whatever the angle happens to be is whatever it is. So magnitude is always 1. So this bit right here just goes to what is the magnitude of e to the negative sigma t going to look like? Well, sigma has to be a real number because it's the real part of s. Is it possible for this to ever be negative? No. So it's just going to look like e to the negative sigma t. So this boils down to 0 minus to infinity of the magnitude of f of t times e to the negative sigma t, and that sigma looks too much like a 6 for my taste, dt must be less than infinity. So it needs to converge to some definite value. And this is true for real values. So for real sigma, is the way to put it. Okay. If sigma c is the smallest value of sigma for which the integral converges, then the region of convergence will simply be all sigma that is greater than sigma c, where sigma c, once again, is the smallest value of sigma that causes convergence. So, luckily for us, practically all physically realizable signals and systems will obey this. So, everything that we can create in a lab should have a Laplace transform. All right. So we have defined the Laplace transform for of a function f of t. Now let's talk about how we get back, right? So mathematically, the inverse Laplace transform is as follows. So the inverse Laplace transform of f of s will be equal to 1 over 2 pi j times the integral from sigma. I feel like I'm missing a j here. Let me look really quickly. Excuse me. Yep. Minus j infinity to sigma plus j infinity. That j looks odd, so let me fix that. Of f of s e to the positive st dt will be our time domain function. I hear whispering and tittering. What's up? Sigma minus j infinity and sigma plus j infinity here. So this integration occurs across both dimensions, or both directions, I guess would be a better way to put it, of the complex plane. How many of you guys know how to perform integrals on the complex plane? None of you. I did it once for a graduate class at this point 10 years ago. Don't remember how to do it at all. I have no intention of relearning how to do it because obviously I haven't needed it since then. So if it were important, I probably would remember. So if we are not going to do this terrible integral, what are we going to do? Well, luckily for us, the Laplace transform of a function and the function form a unique pair. So for every individual function f of t, there is a unique Laplace transform f of s and vice versa. So instead of ever doing this terrible integration to figure out what f of t is based on f of s, we're just going to develop a database of pairs that will let us figure things out and just use those transform pairs to do the inverse operation. So what we're going to do until I run out of steam here is just start deriving those pairs. Okay. So let's start with something relatively simple. Okay. So let's say that my function f of t looks like this. So I have a rectangular step where the height of this rectangle is a, and the time at which my function switches from a value of 0 to a value of a is capital T. How would I describe this function as a mathematical description? So just u of t. So f of t would be a times u of what? T minus capital T. So the Laplace transform of this function is going to be the integral from 0 minus to infinity of a times u of t minus capital T e to the negative st dt. A is a constant term, so we could move that to the outside. So what should this integral look like from 0, where we start things, to t? 0. That part can get thrown away. So realistically, we only actually need to start integrating at capital T. What does u of t minus capital T look like over this interval? Just 1, okay? So we can treat u of t minus capital T as literally just the number 1. So we'll have e to the negative st dt. So that's going to look like negative a over s e to the negative st evaluated at infinity and t, which is just a divided by s times e to the negative st, like so, right? Because this guy evaluated at t is equal to infinity is going to look like 0 minus e to the minus s capital T, and then minuses cancel each other out. Okay. So what would happen if a were equal to 1 and t were equal to 0? I get what? 1 over s. So if we have just u of t, this transforms into simply 1 over x. So we can actually glean some things from this relationship and this relationship, right? So first thing that we can glean from this relationship is that if my function, whatever it is just scaled by an arbitrary constant, my transform is just scaled by that exact same arbitrary constant, right? If my function is time shifted by some arbitrary amount, capital T, I simply multiply my transform by e to the negative s capital T to take into account that time shift, right? So we've stumbled our way into 2 of the properties of the Laplace transform, right? Scaling and time shifting. So taking this into account, what if I had the following signal? Instead of just a ramp function, or excuse me, a step function type thing, we now have a rectangular pulse. How would I describe this mathematically? And the height of this guy is once again a. Okay. So They have the same amplitude, so we're just going to use A. Things turn on at time t1. And since things turn off at time t2, we're going to subtract that second unit step function. Just for simplicity's sake, I'm going to call this AU of t minus t1 minus AU of t minus t2. From this, what should our Laplace transform of this guy be? Yeah, that's exactly why I wrote it this way, so that we could literally do the Laplace transform of this part minus the Laplace transform of this part. Because if I have two distinct functions, I can break up my integral to just integrate each function, right? But I don't even need to do the integral at this point because of the previous example. A over S So that would be for a unit step function, except that its amplitude was A. How do we take into account that time shift? E to the negative S T1. For my second guy, it's going to be the exact same thing, except T2. And we could write this as A to the S times E to the negative S T1 minus E to the negative S T2, like so. Okay. Let's say that we have a function that is an exponential. Let's make this as generic as possible. So let's call this guy just simply e to the negative alpha t u of t. So it explicitly only lives, for lack of a better term, for t greater than or equal to 0. We don't really need to put an amplitude on it since we know that that's just going to scale it by some particular factor. I want to find the Laplace transform of this guy, right? So how's that going to work out? Well, f of s would be the integral from 0 minus to infinity of e to the negative alpha t times e to the negative st dt. What happens when I multiply two exponential functions together? I can add the exponents, right? So that's going to look like the integral from 0 minus to infinity of e to the negative s plus alpha t dt. Okay. Anybody got a beef with this? Yes. U of t is going to look like 1 over the interval from 0 to infinity. Yeah, 5. So how do I do the integral of this thing? Okay. So -1 over S plus alpha multiplied by e to the negative S plus alpha t evaluated at 0 and infinity. Okay. So what does this guy right here look like at t is equal to infinity? 0. What's it look like at t is equal to 0? 1, so we'll have 0 minus 1, so it's just this thing right here multiplied by a factor of -1. So we have 1 over S plus alpha. Okay. So this is going to be useful. What if we have f of t is equal to cosine of omega u of t? There are several different ways that we can do this. Okay? But I want to do this just using what we've laid out to this point. Okay? If you want to see it done by integration by parts, Dr. Walters from the math department here has a great long video of doing it with integration by parts. I'm too lazy for that. Okay. So what I'm going to do is I'm going to play around with trig identities. Actually, Euler's identity here. Okay. So I could literally just throw this into an integral, multiply it by e to the negative s of t, and then do a bunch of math. But I don't want to do that. So do you guys remember what Euler's identity is? We talked about it in circuits 1. It's got a sine and cosine in it. Thank you, Ben, for at least remembering that much. Euler's identity is foundational to the field of electrical engineering because it's what allows us to transform from the time domain where we have sine functions and cosine functions to the frequency domain where everything is expressed in terms of complex numbers, right? So Euler's identity is e to the j omega t is equal to cosine omega t plus j sine omega t. Okay. So using this identity, what should e to the negative j omega t be? So I would argue it should be cosine of negative omega t plus j sine negative omega t. Now, what is cosine of negative omega t equal to? Cosine of positive omega t, right? Because the cosine function is symmetric. What is sine of negative omega t equal to? Negative sine omega t. So if I add these together, what I'll wind up getting is e to the j omega t plus e to the negative j omega t is equal to twice cosine omega t. And from this, we can express cosine omega t as 1/2 e to the j omega t plus e to the negative j omega t. So I would argue that I can use that relationship to say that cosine of omega t u of t is going to be the same thing as, put this here, 1/2 e to the j omega t plus e to the negative j omega t u of t. Or 1/2 e to the j omega t u of t plus 1/2 e to the negative j omega t u of t. So now that I've expressed my function like this as a sum of exponentials, I can just use these results to figure out what the Laplace transform is without having to do a bunch of integration by parts and other tomfoolery that I don't want to do because it's hard. So for this first guy right here, what's alpha? If we compare it to what we were doing up here. No, also not j omega, negative j omega. Okay. So f of s should be, for the first bit, 1 over s minus j omega. What about for the second part? Actually, sorry, because I'm missing a factor of 1/2, right? Up front. Now I want to do the Laplace transform of this part. So in this case, alpha is just j omega. So we would have 1/2 divided by s plus j omega. One over. We could leave it like this, but I see complex conjugates, and so I know that I can fancy things up even further, right? So that's going to look like 1/2 times 1 over s minus j omega, and I'm going to multiply this by s plus j omega over s plus j omega plus 1/2 times 1 over s plus j omega times s minus j omega over s minus j omega also. So I'm going to have s plus j omega in the numerator. My denominator is just going to look like s squared plus omega squared. Same denominator over here. So what happens when I add these guys together? In the numerator, I'm going to have 2s multiplied by 1/2. It's going to look like s. And my denominator is going to be s squared plus omega squared. No integration by parts whatsoever, literally just using the Laplace transform of a simple exponential function and applying it to our signal here because we were able to express it as the sum of exponential functions. Ryder, what's up? Okay, so let's look at what we did up here, okay? So for a generic function, e to the minus alpha t, our Laplace transform is 1 over s plus alpha. So I'm looking for something, whatever I have multiplied by t is going to be negative alpha. Down here, I have j omega times t is equal to negative alpha, which means alpha was negative j omega. Whereas for this part, I have negative j omega times t is equal to negative alpha times t, except for this part, alpha was just positive j omega. Okay, so what if I wanted f of t is the sine of omega t u of t. So let's look back up here, right? So to get cosine, I added these two expressions together, where just the cosine parts survive that process. So how am I going to get the sine part to survive the process? Subtract. Absolutely right. So e to the j omega t minus e to the negative j omega t is going to look like 2j times sine of omega t. From this, sine of omega t is just going to be 1 over 2j times e to the negative j omega t, excuse me, e to the positive j omega t minus e to the negative j omega t. Right? So that's going to look like 1/2 j e to the j omega t minus e to the negative j omega t u of t, or 1 over 2j times e to the j omega t u of t minus 1 over 2j e to the negative j omega t u of t. That's what I'm throwing to this point. Okay. So what should the Laplace transform of the first part be? It's going to be damn near identical to what we just did, right? So I believe we should have 1 over 2j times 1 over s minus j omega. I'll go ahead and put this part here. S plus j omega over s plus j omega. Sorry, f of s. Then we're going to have 1 over 2j, 1 over s plus j omega times s minus j omega over s minus j omega. Like so. Have I screwed anything up? I hear whispering. Anybody see anything wonky here? Okay. So that's going to look like 1 over 2j times s plus j omega over s squared plus omega squared minus 1 over 2j times s minus j omega over s squared plus omega squared. What's going to happen here? Well, the s's are going to cancel each other out, and we're going to wind up with 2j omega divided by 2j. This looks like omega over s squared plus omega. Again, could have done it with integration by parts and spent 45 minutes on it, but we didn't. Excuse me, squared. Thank you. Sorry, I'm assuming that's what you're raising your hand about. All right. Okay, so we know how to deal with a pure cosine function. We know how to deal with a pure sine function. And we put these results together and figure out what to do with a cosine function that has a phase angle, which is a signal that we deal with extremely regularly. Gabriel, you're shaking your head no. You don't believe we can do it? I disagree. All right. So let's say this will be the last one that we work. All right. So let's say that we have cosine of omega t plus some phase angle phi times u. So how can we split this thing up into things that we know the Laplace transform? So I believe that cosine of omega t plus some arbitrary phase angle phi, I'm doing this from memory, so bear with me, should look like cosine of omega t times the cosine of phi minus the sine of omega t times the sine of phi. 97% sure that's right because I use it so often in circuits one, but if any of you guys want to give it a quick Google to make sure I'm not talking about ass here, we can wait a moment for that. I believe that's right. So what is the cosine of phi? Exactly right. And the sine of phi, also a constant, right? So this is just cosine of omega t being multiplied by some constant. So this is might as well just be called A1. This guy over here might as well just be called some constant A2, right? So from this, so cosine, the Laplace transform of just the cosine portion of this should look like S times the cosine of phi over S squared plus omega squared. The Laplace transform of the sine portion of this guy, so we're subtracting it, so I need to put a minus sign here, would be omega times sine phi over S squared plus omega squared. And combining these results together, we wind up getting S cosine phi minus omega sine phi divided by S squared plus omega squared. Yes. So if you're saying that we had sine omega t plus b, let's do it. It'll take just as long as this one did, which was what, 2-3 minutes tops? All right, so I don't use this trig identity nearly as much, so I need to think about this one. I believe it's going to be sine omega t cosine t plus cosine omega t sine t. Now, I genuinely don't 100% remember that that's the correct trig identity. Daniel, you're smiling at me. Did I screw it up? No. Yeah. Let's go under the assumption that this trig identity is correct. If it isn't, it would be easy to fix this thing. Okay. So from this guy right here, we would have omega cosine phi plus s sine phi divided by s squared plus omega squared. S sine. Yep. Okay. Good deal. My old man memory isn't failing as much as I thought it was. Okay. Yeah, I'm going to talk about that. Right. What would be an example of using a Laplace transform? Okay, so let's talk about that here briefly. All right. So for the first few days, we are going to talk about the Laplace transform purely as a mathematical operation like we're doing right now. In our next class meeting, we're going to run through some more of the properties and things like that. And then we are going to talk about partial fraction decomposition and all that kind of stuff to figure out how to deal with finding the inverse Laplace transforms when our S domain function has discrete roots, repeated roots, all that kind of good stuff. You guys look like you're having PTSD already. I promise it won't be that far apart. Okay. Then once we get the rules down and we get used to dealing with these as mathematical constructs, we are going to specifically apply them to circuits. So what we've been doing right here is just taking or finding a Laplace transform for generic segments, right? Generic functions of time. So cosine omega t plus phi is a voltage signal or a current signal in a sinusoidal circuit, right? Where we're not really dealing with steady state sinusoid because we have this u of t here. But we have some kind of background knowledge of how things should work, right? So if we apply a signal like this to an RLC circuit, we should kind of understand what's going on. Well, an RLC circuit will have a impulse response h of t in the time domain that can be converted into a its Laplace transform capital H of s, right? In the meetings from last week, we found that the output of an input function x of t involved with the unit impulse response h of t gave us the output of that signal. Well, in the S domain, convolution is the same as multiplication, meaning that if we can find the Laplace transform of x and we can find the Laplace transform of h, we can multiply those two Laplace transforms together, take the inverse Laplace transform of that product, and it will give us the exact same answer as if we had convolved those two functions in the time domain. So that's why we're doing this. Yes. Yes. So the exam only covers magnetically coupled circuits, or whatever I called it, so magnetic mutual inductances, practical transformers, ideal transformers, and then there'll be a problem or two on convolution. So no Laplace transform stuff for the exam. Yes. Absolutely. That is involved in the ideal transformer stuff. No. Why do you need one? A is equal to N2 over N1. When you refer impedances from the secondary to the primary, you divide by A squared. When you refer them from the primary to the secondary, you multiply by A squared. I say that as if it's simple, and then you guys caught me making a mistake on just that same very thing in the homework solutions. Couldn't do them as late at night as I was doing this. Referring voltages and all that kind of stuff, V2 over V1 is equal to either A or negative A, depending on whether the dot's on the same side or the opposite side. Current relationships follow a similar thing. Why do you need an equation? You don't. So you don't get one. It's going to cover up until what we did before today. So class number 1 through class number 7. Average power for complex or what? What do you mean specifically? So for a DC circuit, it's V squared over R or I squared times R. For a sinusoidally excited circuit, it is 1/2 the magnitude of V squared, or excuse me, the magnitude of the quantity squared divided by R, or 1/2 the magnitude of I quantity squared times R, unless you happen to have RMS phasors, in which point it's just the magnitude of the RMS voltage squared divided by R, or the magnitude of the RMS current squared times R. So when you have RMS values, you use DC relationship. If you don't have RMS values, you need to add a factor by. Now, are you asking about just average power in general, or specifically maximum average power transfer for the homework problem? No. Okay, so maximum average power transfer occurs when the load impedance is the complex conjugate of the Thevenin impedance of the source, or the Thevenin impedance connected to the source. So for you guys' problem, I believe you had 48 ohms plus J32 ohms. So in order for maximum power transfer to occur, the load needs to look like 48 minus J32. And then what's going to happen is the positive reactance of the inductance will be exactly canceled out by the negative reactance of the capacitance, so that the circuit really looks like it's just your voltage source in series with two identical resistors, and then finding average power from that should be a joke for a third-year electrical engineering student. In case it isn't, it's just 1/4 times the magnitude of the voltage squared, assuming you don't have an RMS value. No, excuse me, if you have an RMS value, it'd be 1/8 if you don't have an RMS value, because you need to add that extra factor of 1/2 in divided by the resistance. All of this can be found on my shitty YouTube channel. What else do we got? Yes, Daniel. Did you go from the video? Yes, all of them. Yep. Then
we're gonna have in class portion of the exam Friday, and we're gonna have the take home portion.
I'm not sure when it'll be due. The absolute earliest it will be due would be the following Wednesday.
Okay.
The absolute latest it would be due would be the following Friday. So I haven't decided to give you 5 days or 7 days to work 3 problems. What? I believe so, yeah. I think if that's what the syllabus says, should be 75% for the in-class portion, 25% for the take-home portion. I also have a design project relating to transistors in mind. I need to get that typed out and given to you guys sometime this week. In my head, it's pretty straightforward, but I'll probably just make it due like towards the end of the quarter or something like that, just to give you guys as much time as you need. But realistically, if it works out like I think it's going to in my head, you should be able to do the whole damn thing in 10 minutes.
Thank you.
Gabriel. Fair game, absolutely. So as long as you can remember how to transform from a transformer into the T model, the energy storage relationship should be very, very straightforward because it's just the energy stored by each inductor, add them all together. So as long as you can figure out what currents are flowing through each inductor, you can derive it in literally seconds. Yes. Nothing. Yeah. I mean, they do the relationships, but as far as a problem goes, it's the exact same thing as we did. If I gave you something with a three-phase transformer, which I'm not, it would be for a balanced load, which means you could look at it from a single phase perspective, and it's exactly the same thing that you've been doing. So I'm not going to give you anything with unbalanced loads because then none of the three-phase relationships work. So what's the point? It's doing single phase is just the same as doing three-phase. Everything's just shifted by 120 degrees.
All the problems that they would be solved out.
Yes, absolutely. Well, all of the problems on the in-class portion of the exam will not require the use of a computer. In fact, if you get your computer out, I get to fail you. Yeah, so it is not a it's not multiple choice or anything like that. It is partial credit. So that being said, I just want to be really clear about this. There are like 40 something of you, and there are one of me. So if you don't get your test grades back in like 3 weeks, that's totally normal. You will get them back before the drop date. That is all I am comfortable saying. Actually, let me rephrase that. You will get your scores for exam 1 back before the drop date. That is all I am comfortable saying.